let's move to the next talk just before lunch. So it's by Inar Timiryasov from Lausanne, that is going to tell us about Einstein-Cartan portal to dark matter.
Okay, very good. So yes, thank you. Let me thank the organizers for the possibility to give a talk here. It's always a pleasure to be at Quarks, even virtually. So today we'll be telling about a dark matter production in Einstein-Cartan gravity. So this is one of the series of works done in collaboration with Misha Shaposhnikov, Andrei Shkerin, and Sebastian Zell. So in this work, it's some generalization of the action, like Einstein-Cartan coupled to matter, and some scale invariant generalization. Then we considered Higgs inflation in this theory, and there was a nice talk by Sebastian Zell. Here you can find the link. And finally, this is the paper about dark matter. So here's my outline. I will start from just reminding metric and Palatini formulations of gravity. Then I will move to Einstein-Cartan theory, and then I will discuss the dark matter production mechanism. So metric and Palatini gravity. We all know very well that the lowest order action for gravity can be written in this way, where the Riemann tensor is expressed via connection in this way. And what are the assumptions of the normal metric gravity? So first of all, gamma is symmetric with respect to lower indices. And then it should be metric compatible. So the covariant derivative of metric is equal to 0. And in metric theory, the dynamical variable is the metric. So we vary our action with respect to metric, and we get the Einstein equations. Now, this is not the only formulation of gravity. One can also consider so-called Palatini formulation. So the basic elements are the same. The action is the same. Riemann tensor, again, can be expressed via connection. But now, we also assume that gamma is symmetric. But now, the dynamical variables are g mu nu and gamma mu nu lambda. So when we vary the action with respect to connection, we get a relation between connection and metric. So we don't assume that covariant derivative of metric vanishes. This will be on the equations of motion. And then variation with respect to g mu nu gives us the Einstein equations. So this is summarized here. In metric gravity, this is an assumption. And in Palatini gravity, this is the equation of motion for gamma. Gamma is not dynamical. The only dynamical field is metric, but this is just an algebraic equation. So without matter, both Palatini and metric gravity are equivalent. So we have the same equations of Einstein equations. Okay, then what is Einstein-Cartan gravity? So the story behind even the term is quite complicated. So in the modern formulation which is known to and understandable to us, I think it was basically rediscovered by Keeble in his paper from '61, where he gauged Poincare group. So in the same way as you can gauge any local symmetry of the standard model, SU3 times SU2 times U1, you can also gauge the Poincare group. This will require two elements, which I mentioned further, and one arrives at a formulation of gravity, which is known as Einstein-Cartan Seama-Keeble theory. So before Keeble, Uchiyama tried to gauge the Lorentz group, not the inhomogeneous Poincare group. It was a complicated procedure, and then Of course, everything has been done before by mathematicians. So Cartan has done this in the beginning of 20th century, but nobody understood what he has written. Einstein also worked on this theory, but again, it didn't attract much attention. So before Keeble, it was basically unknown. So what are the ingredients of the theory? Still, the Riemann curvature is expressed via connection. Then the main difference is that the symmetry of connection with respect to lower indices is not assumed. And one can define a tensor, a torsion tensor. So again, as in the Palatini gravity, variation with respect to gamma gives us the metric compatibility, and the variation with respect to G mu gives us Einstein equations. So on the solutions of the equations, the torsion vanishes, and pure Einstein-Cartan gravity is equivalent to metric theory. So all three formulations of gravity in the absence of matter are equivalent, both Palatini metric and Einstein-Cartan. Then, yes, in principle, if one considers the possible action in metric gravity, you can write only this term. If the torsion is if connection is not symmetric, you can add more terms. They will not be very important for us, but still one can add more terms to the action. They can be interesting, for example, from the point of view of inflation, because then you can introduce non-minimal coupling of Higgs to these terms. Still, even with these terms, one can show that the gravity will be exactly the same as metric theory, as metric gravity. Okay, so the Higgs inflation, again, the talk by Sebastian. Then recently there were two papers which appeared almost simultaneously, which considered this action, its generalization, where you add Higgs with some non-minimal coupling here. Every time you see mass Planck, you can add something like Planck plus psi h squared, and this changes a bit prediction of the Higgs inflation. This has been already discussed in Quark's workshops, but we were interested in dark matter here. So before going to dark matter, one other thing which was discussed by Misha Shaposhenkov in his talk here is that in principle, this the action which follows from this Einstein-Cartan or from Palatini is interesting for the mechanism of non-perturbative generation of the electroweak scale. Again, this is not the subject of this talk, but this non-minimal these operators help to smooth the solution of this gravitational instant. Okay, so what about dark matter? We have mentioned that this is the action, but we can also add the matter part, so the fermions. So this is if you want to add fermions to gravity, you need to you need tetrad field and spin connection. In some sense, so suppose you work in Palatini formulation of gravity and you want to add fermions. Then the right way to do that would be this Einstein-Cartan gravity, because anyway you need the tetrads and spin connection, and those are the variables which appear in Einstein-Cartan theory in a natural way. So this is the usual fermionic action with the covariant derivative, and what changes here is that in Einstein-Cartan theory, you can introduce non-minimal couplings. Well, so some extra couplings of fermions to gravity. So in metric theory, this part would be vanishing, but here you can play with gamma matrices to show that these two couplings, alpha and beta, they lead to some non-trivial. They're non-trivial, unlike in metric theory. This has been also realized quite some time ago, and we will be interested in these new parameters which can be added. So those are also like the dimension 4 operators which can be added to theory. From general perspective, they have to be fitted from the experiment, and that's what we sort of will be doing. Okay, so as I told you, on the without matter, the Einstein-Cartan gravity is equivalent to metric theory. However, if you have fermions which have spin, they can source torsion. Then this torsion, again, it's an algebraic equation. You can integrate it out, and you will end up with fermion interactions. How it looks like? Let me introduce vector and axial currents. So X is a standard model fermion. I will also add some singlets which will play the role of dark matter. So if you have alpha and beta vanishing, you will still have in Einstein-Cartan theory, you will still have interactions of axial currents, like 4 fermion interaction with gamma 5 matrices. This is the first place when Einstein-Cartan theory is different from normal gravity. The torsion, which can be integrated out, leads to universal 4 fermion interactions. Moreover, if this couplings alpha and beta are non-zero, you have more terms of this type. Here's the expression. So this expression can be obtained if you take the add fermions to the gravity. You find the solution for the torsion, integrate it out, and get this 4 fermion interaction. Now, the most important part of this 4 fermion interaction is that it is yes. Is there a question? Okay. So the most important part of this thing is of this interaction is that it is universal. So it is interaction between all fermions. So if you add some singlet fermions, singlet with respect to standard model, they still have spin, and they still source torsion, and they will interact with the rest of the fermions.
Okay.
And
dear Zurab, can you turn off your microphone?
Se vuoi puoi spengere la telecamera, Zurab.
Maybe also a host can do that. Okay. Yeah. Thank you. So we have a universal interaction which involves all fermions, and it is suppressed by Planck mass. So in laboratory, it's almost impossible to look for these interactions. If you take, for example, standard model effective field theory, the suppression scale for such operators would be around a few TeV, and here you have Planck mass. So this is all compatible with all experimental bounds and so on, but it can be important in the very early universe. So we have these interactions which involve both singlet and standard model fermions, and we can have dark matter production via these 4 fermion interactions. So standard model particles, X here, they can annihilate to dark matter particles. And yeah, this is the mechanism which we consider. So one can describe this in terms of kinetic theory. This is pretty standard derivation. You write down the Boltzmann equation, and since the interactions are very weak, we'll be mostly we're interested only in freeze-in. So the number density of these guys never reaches the equilibrium value. That's why I don't write the second part of the Boltzmann equation, which shows the annihilation of n back to standard model particles. So, and Fn here is the number density of singlet fermions of dark matter candidates. This is my collision integral, and it includes the distribution of the standard model particles. So this distribution, we need to make some assumptions about it, just to be able to calculate the integral, to compute the integral. So we will assume that X are thermally distributed. So after preheating, everything is in thermal equilibrium. So from this equilibrium, from these fermions, you will create dark matter. So let me go into further details, because it will be important for some consequences. So I can rewrite this equation in terms of dimensionless variable E over T, or momentum over T, doesn't really matter. Then there will be some combination of these non-minimal couplings. It is different for Majorana and Dirac. I will show it a bit later. Then one can show that the only combination which is in the collision integral is this. This is the amplitude. I can do this integral numerically, but there is a very good analytic approximation. So if I take this as Boltzmann distributed, I can do this integral fully analytically, and I will get this result. So we checked numerically that the result for the integral, numerical one, is very close to this form. And what is f of x here is the distribution of the standard model particles. So in principle, the distribution of dark matter will carry some information about the distribution of the standard model particles at very, very high temperatures. So if we at some point will be lucky enough to measure the distribution function of dark matter, we can infer something about details of preheating. And as you can see here, so this looks very much like sterile neutrino production, but it is a bit different. And as you will see here, the distribution of this Fn is proportional to y times Fx. In sterile neutrino, it is not the case, because the mixing depends on temperature. But this is the result, and the production is most efficient and at very high temperature, T production. So it comes in the third power here, where M0 is Planck mass divided by this square root of G effective. So now one can compute the dark matter abundance. It depends, of course, on the production temperature. There is this coefficient, which is a function of alpha and beta. This coefficient doesn't vanish even if alpha and beta are 0. And this is the main result. So now what we can do? We want to have some free. So let me summarize first. This four fermion interaction, which has like purely gravitational origin, can lead to production of singlet fermions, and the mechanism is effective at very high temperatures. So T production should be really high. So can we put this into some framework, so that we know something about preheating? Yes, one natural candidate would be Higgs inflation, because this is a minimalistic setup. We don't need anything apart from the standard model Higgs. I mean, the logic is the following. So we don't know what is the gravity. It could be described by Einstein-Cartan gravity. Then, if we want to stay minimalistic, we consider Higgs inflation. The dark matter is some singlet fermion, and that's it. We don't need anything else. So Higgs inflation, it was introduced by Bezrukov and Shaposhnikov. Then it has been realized that Palatini Higgs inflation has some advantages. In particular, it has the parametrically larger cutoff. So it's M Planck over square root of psi, where psi is the non-minimal coupling of Higgs, H here, to gravity. So in this theory, Higgs plays the role of inflaton. And another thing, it is known that the preheating is almost instantaneous. So the temperature of preheating can be very, very large. That's what we take. We consider Palatini Higgs inflation and take the preheating temperature. So the dark matter production is mostly efficient right after preheating. So we take production temperature is the preheating one, which is given by this expression here. And now we can compute the dark matter abundance. So as you remember, this CF was a function of alpha and beta, this non-minimal Fermi couplings. We can make some assumptions about these couplings. The first assumption is this alpha and beta are equal to 0. As I already told, that the 4 Fermi interaction is still there, but it is suppressed by Planck mass. And in this case, the correct dark matter abundance is obtained for very heavy fermion, 10 to 8 GeV. It is quite interesting that the same mass range is in the same mass range. The fermion can be created just from direct graviton scatterings, or just in the expanding universe, it can be created because of the, varying Bogoliubov coefficients. But another assumption is the following. Let's say, so this alpha and beta, they introduce some cutoff in the fermionic sector. So what if this cutoff is the same as the cutoff of the Higgs inflation, Planck mass over Xi? We can do that. So we assume that alpha and beta of order of Xi, and then we get an interesting coincidence that the right mass range is in keV scale. So this is of order of 1 if we take production equal to reheating, and this is again of order of 1. This term is also of order of 1. One can show, and then the dark matter, the correct abundance of dark matter is reached for keV scale dark matter. This is of course very interesting, because we can say something about distribution of keV scale dark matter. Before doing that, let me put this into like complete framework of the new MSM. So the new MSM is the extension of the standard model by 3 right-handed neutrino. One of them is the dark matter candidate. It is singlet. And 2 others, they are responsible for the neutrino masses via seesaw and for leptogenesis. So since there are only 2 mass differences which are observed, 2 heavy right-handed neutrinos are enough to generate the mass differences in neutrino. So this guy can be almost decoupled from the neutrino sector. I mean, the mixing can be very small. It doesn't contradict to anything. And this is the plot from sterile neutrino dark matter review by these people, and one can see the following. So these bounds here are X-ray bounds, because if you suppose that if you have some mixing of sterile neutrino with normal neutrino, this mixing gives you decay to neutrino and photon. So one can expect some X-ray signal. However, in the case of the mechanism which we consider here, the mixing is not needed, because the dark matter is produced in by some absolutely different mechanism, so the mixing can be small. So you basically don't care about this bound. What you do care is the Lyman alpha, which studies the distribution of light dark matter. So free streaming affects the Lyman alpha, and if we would be extremely lucky, the dark matter is somewhere in this range, and it will be, and we can infer its spectrum from the Lyman alpha observations. Now one can ask, okay, so we produce N1, but in the same mechanism we also produce N2 and N3. Would this change the leptogenesis? And the answer is no. This practically does not affect the leptogenesis, because we can do the following exercise. We take the mass of this guy and assume that this is it constitutes the whole of dark matter, and then we can say, okay, the number density of N1 and N2 and N3 are equal. What is the how many N2 and N3 we have? And one can see that it is like 1% of the equilibrium number density. So this will not change the leptogenesis. This figure here illustrates the following. I can start leptogenesis with vanishing HNL number densities, right-hand neutrino number densities. This is white region here. or I can start from thermal distribution for N2 and 3, and then the leptogenesis works in this region. So and here I start not from thermal, but like from 1% of the thermal distribution. So leptogenesis basically is not affected. And next thing is the momentum distribution. Yeah, I'm close to the end of the talk. So as I told you, this mechanism predicts certain momentum distribution of N1, and this is different from the other production mechanisms. So here I show the resonant production. Resonant production requires very large lepton asymmetry at low temperatures, which in the new MSM it can be generated only provided some severe tunings. This is the orange line. So the green line is just the thermal distribution. Okay, it's excluded, but still many, for example, Lyman alpha people consider this as an example. And the blue curve gives you the distribution of N1 in this Einstein-Cartan mechanism. And you see it is very different from both of them. So if we are lucky enough and the dark matter is sufficiently light, we can even distinguish the production mechanism via its spectrum. Okay, so that's basically it. This is my summary. And Einstein-Cartan theory is equivalent to metric formulation in the pure gravity case. However, if one considers fermions, there are new 4 fermion interactions which are universal, and these interactions can give you a new dark matter production mechanism. So yeah, that's it. Thank you very much.
Okay, thank you, Inar, for this nice talk. Questions? Igor, please go ahead.
Yes, Inar. Thank you for a nice talk. What is the difference in your mechanism with, say, direct production from the inflaton? This mechanism, you know this mechanism, right?
Yes. So if the inflaton is coupled, so here we assume that the inflaton is here. So if you want to stay minimalistic, you assume that the inflaton is just Higgs, and then there is a preheating, and all standard model particles are created, and the dark matter is created from the standard model particles. So it's just 4 fermionic interaction, which leads to dark matter production. Does this answer your question, or maybe I misunderstood it?
I don't know what happens with this minimalistic model when inflaton is Higgs, but if it's just general inflaton, then I can couple sterile neutrino to inflaton directly, and it's not forbidden, and then it's different mechanism compared to thermal production and with specific distributions, momentum distributions. The question is whether you can distinguish whether it was Einstein-Cartan or direct production. Okay, you convinced us that you can distinguish with thermal production in principle if we are lucky, and we can reach all these sensitivities, but can you distinguish with inflaton, direct production from inflaton?
So I guess again it depends on the mass of these fermions. If they are light enough, I would so from the inflaton it is just the case of the inflaton to this singlet fermions, right?
Yes, right.
So you have one more scalar in the theory, which is the inflaton, and it can couple directly to.
Sure. Yeah, if you haven't studied this question, then we can discuss later.
No, I haven't studied, but
fine.
Okay, David.
Hi, I have a couple of questions. With the so non-minimal couplings in the scalar sector, arise in string theory for like a dilaton coupling or like in the alpha prime expansion. Does string theory also give you non-minimal fermion couplings like you have here?
So this is a very good question. I'm not sure I can answer this directly because I didn't go through the where was it here? So yeah, these people study such couplings, but again, the philosophy is that those couplings are not forbidden by anything, so they must be there. I'm not sure if you so in general in string theory, I think the description of gravity which you get is this Einstein-Cartan description.
Right. That's right. So.
I cannot tell you with certainty what about this alpha and beta. So yeah.
Okay, and then the other part of my question is when you get these new axial current type couplings, do they also couple to gauge fields, and do they change the anomaly structure of the theory?
No. So okay. So those couplings they are only via torsion. So the torsion, it is sourced only by the fermions. One can show that if you have gauge invariant vectors, it does not source the torsion. So there will be no coupling of gauge fields with this fermionic currents.
Okay.
So gauge invariance protects from having these couplings.
Okay, thanks.
All right. So there is also a question from Dmitry Levkov.
Okay, thank you for the talk, Inar. I have a question about the couplings which are now displayed. Do you hear me? Yeah.
Yes.
Yes. So if alpha equals 0 and beta equals 1, your couplings vanish. So does this correspond to the kind of chiral fermions? Does this mean that left-handed fermions do not couple at all?
No. So alpha. Yes. This is indeed. This is a very specific choice of the parameters, and in this case, no. The fermions will not. I mean, there will be no such four-fermion interaction, but because there will be the cancellation. So the fermions still source this torsion, but there will be cancellation here.
Yeah, but does this case correspond to left-handed fermions? So left-handed fermions somehow do not couple to torsion. In the previous transparency, you have a definition of alpha and beta in front of gamma 5. Yeah. So if beta equals to 1, then this kind of Lagrangian for left-handed fermion, no?
No. So here psi. Yes, it doesn't. No. So you have this I here. So it's not left hand. It is a bit tricky. So you can think of psi as a chiral fermion, either left or right. So this I beta, it's not like a projector on the chirality, because then if you yeah, the answer is no. It does not correspond to chiral fermions. It is a bit more tricky. You have to use some, yeah.
But
this is some linear combination. So
why is that? Because this is a bit funny, because if you choose your metric to be the flat metric, right, then I think Dimitri is right. I mean, this should look like this should look like an axial current, right? So I didn't get your last point actually. Why it doesn't correspond to chiral fermions?
So you have this I here. So suppose beta is 1, but it is real. So it's like 1 minus I gamma 5. Then you can, we have this here. Yes, then you can insert, so maybe I don't have enough formulas on the slides. So if you have a flat case and vanishing torsion, if this guy, so vanishing torsion means that gamma is symmetric. This will give us some symmetry property of the spin connection, and you can work out this combination of free gamma matrices, and you will see that this is zero if this guy is like symmetric in the indices. If this guy is not symmetric, one can show that yeah, it leads to a coupling of the torsion tensor, which was defined somewhere here, of this torsion tensor to the fermions. Where is it? Here.
Okay.
Psi bar psi.
So somehow these torsion terms sort of like mixed up the left and right in some sense, right?
Yes. Yes.
Yeah. Okay. Okay. Thank you.
Mm-hmm.
I don't see any other question here. So if that's the case, let's thank Inar again for this nice talk.